chart. We're missing Okay, folks. It's that time. I'm going to go ahead and get started. The very first thing I want to do is I want to I don't know if it's a warning or what you want to call it, but you will want to make sure that you are watching the flipped classroom videos for next week. The reason is because, I hate to say it, but it's about to get real quick. The content is about to get tough in the fact that it's less conceptual and more mathematical. And if I am going to have time to walk you through the mathematics so that you are comfortable with the mathematics, then you've got to do the legwork of watching the videos ahead of time. Now, yes, the videos will walk you through the mathematics to some degree, but as you haven't noticed, they are PowerPoint. And so how good they are at walking you through a mathematical process is another story. So, like I said, whether you want to take it as a warning or whatever, that's up to you. But it is going to get significantly tougher from a mathematical standpoint. And if I am going to do some problems with you, you've got to do that hard work ahead. Now, I have tried to develop so on Monday, what we are going to start doing is we are going to start doing concentration conversions. Now, you've had experience with molarity. You may have had experience with percent composition, but we're gonna start talking about molality, mole fractions, which you should have a little bit of experience with in gas laws. But we're also gonna look at how to convert between all of these. So what I've done is on the front page, you have a list of the formulas I'm gonna give you on the test. On the back page, you're not gonna get that. But it kind of walks you through how to do a conversion between the different concentration units. And I will use this when you start getting into calculations on methods. So I'm giving it to you in advance so that as you watch the videos, you can maybe see how it guides you through it on the back page of the document. Any questions? So today is the last, well, it's not the last day of conceptual because you get conceptual all throughout, but it's the last day where we're not really going to be doing much in the way of mathematics. Otherwise, we do a lot of mathematics. Oh, I should tell you one more thing before I get into today's, because today's lecture is actually going to be relatively short. So we'll probably get out of here a little bit early. I posted yesterday the Blackboard for next week. On that front page, before you click into the folder, at the very bottom, you will notice that 2 weeks from today is your first exam. I'm already telling you 2 weeks from today is your first exam on the 20th of September. I'm already telling you what's going to be on the exam. So you have plenty of warning. One of the things that I will state regarding the exam is there's going to be about a week's worth of information that we go over that will not be on the first exam. It will come in on the second exam. That's because when I looked at the exam and looked at the fact that we only have 50 minutes to take an exam, I was concerned about how long it was going to take. Because there's a lot of information, a lot of, especially coming up mathematics. And so it's only going to be over chapters 11 and chapter 13 information. Chapter 14's information we will start. I will lecture over prior to your first exam, but it's the chapter 14's information is not going to appear until the second exam. So that's the other thing I did yesterday, trying to help prepare you. So a couple of big things. Question, yes.
What chapter is this?
This is chapter 13. So yeah, the sheet I just handed you is chapter 13's information. This is on the exam. So you have a little bit of time. Any other questions? I try to be very upfront with you guys. I'm trying to let you know way in advance what's happening. so that you're not thrown for a loop in the last, what feels like hour. So I've announced this watch videos so that I can do nothing but problems next week. I've announced, I've given you this sheet which will help walk you through problems. I've discussed the blackboard and how it lists the activity exam. The only other thing that I was going to mention is the laboratory. Next week will be the first time you have a pre-lab that is due. And the pre-lab is due when you walk in the door. So something to do over the weekend or Monday at the latest is the pre-lab for next week's lab. You should have the background knowledge necessary to do the pre-lab because it is all related to intermolecular forces. So, any questions about that?
You turn that in online or in the lab?
No, it's turned in the lab. So when you walk in lab, you'll turn in a hard copy. So yeah, let's talk about lab a little bit, just so that you know how I'm going to work the lab. Number one, you will be in lab partners starting Tuesday. When you walk in the door, my TA is going to be looking for closed-toed shoes, long pants, which I'll try to remember to remind you on Monday, to pack a pair of sweatpants or something in your backpack, and your goggles. You will turn in your pre-lab when you walk in the door. During the lab, you'll work in partners. You and your partner will turn in one data, results, and conclusion sheet on Wednesday of next week. And then I'll basically shuffle it all together to get the lab completed. So I'll put your pre-lab with your data and results sheet. So that's how I run labs. So it's just one lab report that gets turned in for the payer. But the pre-lab, each individual has to do. In lab, I do expect you to participate. I will make comment if I see one person doing all of the work and the other person sitting on their haunches doing nothing. You are expected to participate, so therefore you should know what's going on. Any other questions? Anything I'm forgetting that you have an inkling to know? Okay. So we're going to get started into today's material then. And we started the conversation on Wednesday about solution formation. And solution formation, to a large extent, is based off of intermolecular forces, like dissolving light. Polar wants polar, nonpolar wants nonpolar. Now, you can get, depending upon the size of the molecule, you can get nonpolar to dissolve a little bit into a polar solvent, such as CO2 into water. But once you get to these bigger molecules, such as octane, which is 8-carbon alkane of carbon and hydrogen only, you don't get it to dissolve in water because the forces are just too different. And it's too big, the octane is too big of a molecule. But small gas molecules we can get to dissolve in water. Now, One way we can get gas molecules to dissolve in water, which is how carbonated beverages are made, is to put them under pressure. So here you have a diagram. You have some gas that resides above the liquid level. Under whatever this pressure is, some of that gas has been dissolved into the liquid. Now, if we take this movable piston and we push down on the piston, we will have decreased the area above the liquid level. By decreasing the area above the liquid level, what it means is those gas molecules, which are zinging around and moving around and bouncing around, they're going to encounter that liquid level more frequently. And so by the movable piston, by putting pressure on it, those gas molecules that are above the liquid level, some of them are going to go ahead and go into the liquid. This is done until what is a new dynamic equilibrium is obtained, where you have a certain amount of gas above the level and you have gas in the liquid. Now, why is it called the dynamic equilibrium at the start and at the end? The reason is because when you're looking at this cylinder, as I mentioned, these gas molecules, they're bouncing around, they're hitting the walls, they're hitting the liquid, and with every collision, they lose some energy. And so some of those go into the liquid level because they're less energetically favorable. But they don't stay there. They go back out of the liquid level. And so it's a dynamic equilibrium because the amount of gas molecules that are entering into the liquid level is equivalent to the amount of gas, I shouldn't say equivalent because that's a wrong term. The amount of gas entering the liquid level stays constant, while the amount of gas that was in the liquid that is escaping stays constant. So that's why it's called the dynamic equilibrium, because the amount of gas inside the liquid and the amount of gas above the liquid no longer changes. When we first apply the pressure to the cylinder, we change that the amount of gas going into the liquid level. We're going to increase the amount of gas that goes into the liquid level. That's why you see a lot more of the black arrows pointing down. But after you have gotten this, yes, you'll have more gas in the liquid level, but at some point, again, you're going to reach a dynamic equilibrium where the amount of gas going into the liquid does not change, and the amount of gas coming out of the liquid does not change. That's what we mean by dynamic equilibrium, is the amount of gas appears to be the same constantly. But gas is always or molecules are always in motion. So some are going in and some are coming out.
So that only increases until like the new equilibrium is
It will establish it'll increase until it establishes a new equilibrium. It's not the same equilibrium as before. It's going to be a new equilibrium. But all it means with equilibrium is that the quantity appears to be the same on both sides. So the amount in solution appears to stay the same. But again, molecules are in constant motion, so some are going in, some are coming out. Other questions? So one way we can increase the amount of gas in a liquid, or increase the solubility, because that's what we're describing. We can increase the solubility, we can increase the amount of gas by applying pressure. So applying pressure increases the amount of gas in solution. Now we can determine the concentration of gas in solution using Henry's law. Henry's law states that the concentration of a gas in solution is equal to K times P, where K can be found in a table with Henry's law as a Henry's law constant for that gas. And P is the partial pressure of that gas. Henry's law can help us answer a question that we all know occurs, and that is, why do soft drinks go flat after being opened?
Because the pressure is a harsh pressure no longer there. So
That's because the pressure is no longer there. And so basically from a conceptual standpoint, once you pop that tab, or once you open the bottle, what do you hear? You hear the sound, which is gas escaping. Now, if you look at Henry's law constant, it's very easy to understand why the gas escapes. Uh-oh. Because Henry's constant, the constant for CO2 in water is only 3.4 times 10 to the minus 2. And that would be in atmospheres? No. I'm sorry, that's in molar per atmosphere. .034 moles per liter is all we're talking about that of CO2 that will go in water at 1 atmosphere. 0.034 moles per liter of CO2 will go into water at 1 atmosphere. That's not a whole lot. So when it is bottled, it has a partial pressure for CO2 of 5.0 atmospheres. That means that the concentration of CO2 when it is bottled is equal to Henry's law constant times the pressure. The constant is 3.4 times 10 to the minus 2 molar per atmosphere times 5 atmospheres, or in other words, the concentration when it is bottled is 0.17 molar. Now, when it is under normal pressure, of 3.3 times 10 to the minus 4 atmospheres CO2, then the concentration is equal to the 3.4 times 10 to the minus 2 molar per atmosphere times 3 times 10 to the minus 4 atmospheres. Or in other words, the concentration is 1.02 times 10 to the minus 5. If you think about that, that means opening a bottle and letting it set causes a loss of 0.1699 molar CO2. In other words, almost all of the CO2 is lost because it is under a much lower pressure.
You just took the local or extracted from the partial pressure.
I did.
The partial pressure is only the pressure that it has in like a container.
partial pressure is, it's called partial pressure because not only do you have CO2 gas, but if you'll recall from when you did the peroxide lab in college chemistry 1, you also have water gas above the level, so both of them are applying their own pressure. So that's why it's called a partial pressure. But basically, what happened is once we seal this up, it's under 5 atmospheres of pressure. We have 0.17 molar CO2 in this water. You unseal this thing, and all of this gas escapes. This and the gas in the liquid escapes. Now, it takes a little bit of time. I mean, obviously, you can open a 2 liter and it's not going to go flat immediately, partially because the way things are designed. But basically, you pop this off completely. The popping is this gas escaping. So the initial gas in the head space escaping. But if you let it sit and it comes under a normal CO2 pressure in the water, this drops down to 1 times 10 to the minus 5 of what's left in here. And so you have almost the entire amount of CO2 that's escaped into the atmosphere.
So why does he subtract the normal pressure from the partial pressure? Why was it the other way around?
What I subtracted was bottled Coke, which is fresh. From that bottled Coke, which is fresh, I subtracted out the amount of CO2 that would be left over under regular after it sits. And so you could see that 0.1699 ultimately escaped.
So when you say under normal pressure, that means it's after it's open?
After it's opened, after it's just sitting there in the atmosphere for however long to go flat. So again, key takeaways. What's the key takeaway? The key takeaway is gases are under a dynamic equilibrium with the liquid in a sealed container. If you want to increase the concentration of the gas in solution, you put the gas under pressure. Placing the gas under pressure is going to initially drive more gas into solution until it establishes dynamic equilibrium again. Questions? Okay, so with respect to gases, we can affect the concentration 2 different ways. We can affect it with pressure. The higher the pressure, the higher the solubility. But we can also affect the amount of gas using temperature. Now, I want to, before we get, I mean, this graph shows what happens, but I want you to think about another scenario. We're going to go back to a can of Coke. It's a closed can of Coke. And I leave that can of Coke in the car on the hottest of August days, running up around 105 to 110 degrees outside. People are laughing. What happens to that can of Coke? Huh?
Oh, was it open or?
It explodes. It explodes. You're taking your car to get it cleaned. It explodes. Now, why did it explode?
Much pressure.
It built up too much pressure. Why did it build up too much pressure?
Temperature increases like the movement of the gas in this.
Temperature increases the movement of the gas. Where's the gas gonna head? It's not gonna go back in the solution. It's gonna go into that little bitty headspace. And at some point, the metal can no longer handle the pressure that built up. This shows you the exact same thing. This x-axis is temperature in degrees Celsius. And we have a variety of gases. We have nitrogen gas, methane gas, carbon monoxide gas, oxygen gas, and nitrogen monoxide. Every single one of those illustrate that if you increase the temperature, you're going to decrease the solubility, because the y-axis is describing the solubility in milligrams per 100 grams of water. So the y-axis is milligrams of gas per 100 grams of water. And you will notice that it decreases with increasing temperature.
So, but we also just said pressure increases slightly.
Pressure increases solubility, but temperature decreases solubility.
So what happens if you freeze it? Is it all solid?
Well, if you freeze a can of Coke, it explodes, but it's due to the expansion of water rather than gas.
Wait, so temperature increases pressure, and pressure increases solubility?
Okay. So. What you have to think about is when I was describing the pressure, I physically increased the pressure to get more gas in the liquid. In this particular case, we're holding the pressure constant. So we're not increasing any more pressure. It's just holding constant, technically. So the can of Coke is a closed container. It's not under any more pressure than it was already under. So we're not applying any more pressure to it. It's held steady. At this point, pressure and temperature work simultaneously. Yes, you increase the temperature, you're going to increase the gas that escapes from the liquid. That's the other part of the story, is we were looking at how much can be in the liquid. You increase the pressure, yes, you should get more gas in the liquid. But if you increase the temperature, less gas can be in the liquid because of the speed at which the gas molecules move. There's a happy medium, and that's why the drinks are bottled under 5 atmospheres. There's a happy medium between temperature and pressure at which you're gonna get the maximum amount of gas in solution. But if you change either one of those, you can increase or decrease, in this case, decrease the amount of gas that goes in solution. So if you increase the temperature, the amount of gas in solution is going to decrease. But we were talking, our can of Coke originally was at 25 degrees Celsius. So it was under ideal pressure, under ideal temperature. Did that answer your question, or did it make it more fuzzy?
So essentially, is it because it increases like the kinetic energy in the gas molecules? So even when they hit each other, it doesn't decrease and then the water can't absorb it?
Oh, so the question is, increasing temperature increases kinetic energy. That is a given. Yes, when the gas molecules in gas phase collide, some of them are going to go into solution because they don't have as much kinetic energy. However, because we increase the temperature, we've increased the number of gas molecules at that high kinetic energy. And so that's why it explodes. So it's not gonna, again, there's gonna be a dynamic equilibrium reached unless that dynamic equilibrium is just too, the pressure is too high for the container, and then it explodes. So you can always go up a little bit. I mean, we have Cokes at 98 degrees Fahrenheit, and they don't necessarily explode, but once you get up higher, it explodes because you're giving more and more kinetic energy, and they just cannot go back into solution. Or enough of them cannot go back into solution is more the case. Questions? Gases are, so again, key takeaway. Increase pressure, you increase the concentration of gas in solution. Second takeaway, increase temperature, you decrease the amount of gas in solution.
Since like whenever you increase the temperature to dissolve a solid in a liquid, can you decrease the temperature of a gas to dissolve more into
Yes.
an oversaturated?
Yes, we can decrease temperatures of gases to get more carbon dioxide into solution, or more gas into solution. So yes, you could decrease the temperature and it would increase the concentration.
You call that supersaturated like you would a solid?
I mean, technically, if it's at 20 degrees and you have, let's say, carbon monoxide here, the red line. If it's at 20 degrees and you have more carbon monoxide in solution than should be there, yes, you have a supersaturated solution. If you have less carbon monoxide than should be there, you have an unsaturated solution. And that would be the level of saturation. So yes, you can have supersaturated and unsaturated the same as you can for a solid. But in order to get the supersaturated solution, you're going to have to play with the pressure. Again, they're not independent entirely. They're not independent. Which actually brings us up to the next one. Which is solids in solution. And I just pulled one off the internet. And you're going to actually have to answer some questions. I'll keep the questions about gases fairly straightforward. Because there are two factors that really come into play with gases, pressure and temperature. But let's talk about a solid. So what was just mentioned is you have three solution types. You have an unsaturated solution. An unsaturated solution occurs when you can dissolve more into the liquid. More can go into the liquid and it not fall out. A saturated solution occurs at that point where the maximum amount of solid is in solution at that time. You've hit the max. Now, as was stated, you can, under the right conditions and with the right substances, get supersaturated solutions. A supersaturated solution means that you have more in solution than should be there at that temperature. When you're looking at these types of graphs, if it falls below the line, at that temperature, it's an unsaturated solution. If it hits the line at that temperature, then it's a saturated solution. But if you are above that line and you have it and it's in solution, then you have a supersaturated solution. So let's talk about some examples. By the way, the markers over here, they go up just like from over here, they're going up. So I will point out the line for you as I go. The x-axis represents temperatures in degrees Celsius. The y-axis is the solubility. How many grams of solid can be dissolved in 100 grams of water? Now, let's say I have 175 grams of glucose in 100 grams of water. Glucose is this line. And I have 175, and I'm at 20 degrees Celsius. I'm right there. Wait, no, I'm right there. What type of solution do I have? This would be supersaturated because it is above the glucose line at that temperature. Okay, let's look at 150 grams of ammonium nitrate. Ammonium nitrate is this purple line. Have 150 grams in 50 grams of water. This is a little tricky. I have 150 grams of ammonium nitrate, which is this purple line, in 50 grams of water. To be able to use this graph, what am I going to have to do? I got to double it. So I don't have, so yes, I have 150 grams of ammonium nitrate in 50 grams of water, but that means I have 300 grams of ammonium nitrate in 100 grams of water. So 300 grams And I'm looking at 20 degrees Celsius. 300 is way up there. And it is super saturated. Now, we're going to find that for the most part, dissolving an ionic compound in water is an endothermic process, meaning you have to add energy to get quantities to dissolve. But there are some ionic compounds that are exothermic. What would be an ionic compound that's exothermic that's up there? This is potassium sulfate. This is sodium sulfate. This is ammonium chloride. This is sodium chloride, and then the blue line is lithium sulfate. So which ones? Lithium sulfate is exothermic, meaning if I dissolve lithium sulfate I don't need to increase the temperature, because if I increase the temperature, I'm going to decrease how much lithium sulfate can be dissolved in water. Whereas most of them are endothermic, you increase the temperature, you increase the amount that can be dissolved. Okay, I will see you on Monday. We'll pick up briefly with another couple of examples, and then I will get into talking